Thank you very much for the introduction. Thank you very much to organizers for inviting me. It's a great honor to me. I will speak about topological connection in ultrafast molecular chirality. First of all, I would like to thank my amazing co-authors. I've been fortunate to work with very creative people. So Nicola Meyer, a postdoc on the way to King's College, Nimrod Moiseev, a very dear colleague in Technion Haifa, and it's also nice to see you while here. Alex Laura, PhD student, Pierre de Clever, we collaborate, of course, known in this audience very well. Sorry. Emilia and Margarita, King's College. Yeah, my fabulous chiral team, Andres and David, they are both here. Postdoc Philip Flores, Astrid Lund, the bachelor student, and Stefanos Kallstrom and Misha Ivanov. So I will talk about chirality. You had several chiral talks already from David, Andres, and Yuval, and I'm just, as a reminder, show these two funny round men, which is Tweedledum and Tweedledee. You may remember them from Lewis Carroll book, and they are chiral. You can see this by comparing them, and they keep chiral molecules in the chiral hands. But what is more is that all of us, we are all chiral. Not only my amazing co-authors, but all of us, and we are chiral because all living matter maintains an antimeric axis. So we have not equal amount of left and right molecules in our body. And this is crucial for functioning of the organism, for stability of proteins. So what is more is that abnormal amount of an antimeric axis has been in living matter, has been recently related to biomarkers for diseases. So what one desires right now is to have a very precise but also high-speed methods for distinguishing enantiomers. And although there are amazing and exquisite methods in chemistry which rely on thermodynamics and kinetics, they are very precise, but they are slow. And of course, light is the fastest agent that interacts with matter, and therefore optical techniques, they outpace the chemical techniques in speed. But there is a usual problem with optical techniques is that we know from 19th century that we can probe chiral molecules with chiral light. Circularly polarized light is chiral because the electric field vector makes helix as light propagates in space. But there is a problem that the scale of the chirality of this helix is too large with respect to the scale of the chirality of the molecule. So this mismatch makes distinguishing left and right in microworld extremely challenging. So what we learned from this slide that chirality of light is non-local. And it is normal to have non-local chirality because chirality is a property of an object, extended object, which is defined by the orientations of the mutual parts. But what if we just think about compactifying chirality? Did you think about local chirality ever? So I will give you an example on the slide of a local chirality. What you see here is the electric field vector, which traces chiral three-dimensional shape in time, in space. So within one cycle, the electric laser field can draw this chiral figure. The chirality is temporal, it's encoded in the shape of the Lissajous figure, and it is completely local. What is, you can create such light using multicolor fields, but how do you characterize this light? To characterize this light, you can think of just a question how to characterize chirality of this three-dimensional chiral figure. And you can do a very simple thing. You can take 3 snapshots of electric field vector in 3 consecutive moments of time, and then create a triple product like this. And we know that triple product characterizes the trajectory which goes out of plane. So the moment is non-zero, you know the trajectory went out of plane, so it became chiral. But what you can do, you can average over the period and demand that this quantity is non-zero on average. You can also write it in the frequency domain, and then it clarifies the meaning of this correlation function. This is correlation function of the lowest order that can characterize locally chiral light. What you have here is the triple product of three non-complanar field vectors at three different frequencies. So what you can do, what it shows, it's actually a very important quantity because it characterizes light's chirality and the strengths of an anti-sensitive light-matter interaction in electric dipole regime. Higher order correlation functions, you can build higher order functions by adding here scalar products. They characterize the strengths of an anti-sensitive interaction in multi-photon processes. So what I will talk about in my talk is about various ways of combining chirality and topology. And you probably know that in chemistry it has been actually already combined, but in structure. So what you see here, topology represented by these nodes. So they are quintessentially chiral and topological objects because left chiral node cannot be continuously deformed in the right chiral node. So they are both chiral and topological. What has been done in chemistry that people managed to synthesize such chiral nodes from the molecules, and topological stereochemistry in the end led to the amazing molecular machines. So what I would like to suggest, and the question that I will address today, is it possible to connect topology and chirality in dynamics, not in structure, but in dynamics, kind of locally. So idea that is behind this activity is that we already know how to create extremely efficient chiral observables by using, by relying on electric dipole approximation and using ultrafast concepts such as, for example, temporal chirality. And it would be really nice to add a topological dimension to it because topology is known to be associated with robust observables. So this is the goal that we have in mind, and today I will tell you, and I also wanted to say that combining chirality and topology at the local level is a very new topic, and there are two works from the other groups that I think are very interesting, and I really recommend to check it out. So I will tell you today about three ways on how one can connect chirality and topology. First, linking this two geometrical properties via light. Second, via ultrafast electronic response. And third, via non-Hermitian dynamics. So I start with the light. And I told you already that we can create light which is locally chiral, which means it's chiral in every point in space. Now, if we can make light with such property, we could also decide to control this property in space. So give light different chirality, different handedness, and different points. So what we have done, we decided to create chirality vortex. And to do this, you basically just need to combine the concept of local chirality, so three-dimensional chiral trajectory of Lissajous figure, with the vortex beam. So what you can do is, for example, one of the realizations that Nicola came up with is the circularly polarized combination of right circularly polarized and left circularly polarized omega and 2 omega beams with our optical angular momentum 1 and -1. So what you do, you put these beams together, they co-propagate, and then you tightly focus them, and what happens is that longitudinal component develops, and this is precisely the component you need to create local chirality. This is the Lissajous figure of this light. And what we can do next is to explore its properties. So first of all, what I show here, this is the polarization plane of this light, and it has intensity, has this donut beam. So yes, this is because this light is topological. It has a topological charge, which I will explain a bit later. So now this is what you see, the correlation function that I introduced before. It's a chiral correlation function that shows where the light is locally chiral. And you can see that this is the modulus of this function, and that locally chiral everywhere where it is non-zero. Now, the topological charge is actually recorded in the phase of the chiral correlation function of light. And you see this phase here. It's also in the polarization plane. And what you see here is that the phase of this function goes from 0 to 2 pi 6 times as we go around the vortex. So the vortex is the point where intensity is 0. What it means that the phase of this chiral correlation function has two components. One is global topological, which is proportional to topological charge times azimuthal angle, and the other is chiral locally, the component, the phase, which defines the handedness of this light in every point here. So the topological charge can be analytically expressed by a very simple expression which shows that it's a highly tunable quantity. And in this particular realization, we choose 6, and you see that this is a combination of orbital angular momentum of 2 omega and omega beams and spin angular momentum of these beams. Now, what do we get in the observables? We calculated the highly nonlinear optical response, high harmonic generation, and we did it for function. And what you see on the right is right function, harmonic 18, and left function, harmonic 18 on the left. And what you see here, that there are 6 hot spots, and this happens because we have topological charge 6. What you also see, if you look hard, that they are rotated from each other, and they are rotated by the angle, very large angle, angle 30 degrees, and actually the angle of rotation is topologically protected because it is pi divided by topological charge. So the oscillation that you see here, it's actually determined by this phase factor. Depends on topological phase, so psi here, that's why we see 6 spots, because this is the only parameter which depends on azimuthal angle, the chiral phase, and the molecular phase. And this phase is specific for every specific molecule, and the molecular information apart from molecular handedness actually is recorded here. So now you can also look at the far field image, and it also 6-fold, of course, but what is very interesting for us is to test the robustness of our signal. So what you see here are the 2 signals, again for right and left function, but now in the far field. And if you would like to find a simple way to find the difference between them, you could observe that when there is a minimum of the right, there is a maximum of the left, which means that you can simply take a Fourier transform of the signal with respect to frequency 6, because you have 6 oscillation, and because here you have minimum and this maximum, the phase of such signal will jump by pi when you go from one enantiomer to another. So we will see how it works, but before I tell you, I have to introduce, or maybe again remind you about the enantiomeric axis. It's the difference between left and right molecules in the mixture. And sometimes it's challenging to distinguish very low amounts of enantiomeric axis, and that's why we decided to plot an enantiomeric axis as a plot the phase that I have just described as a function of an enantiomeric axis. So the black curve here represents this phase. I told you that it changes from one value, jumps by pi from left to right, which means that when an enantiomeric axis is negative, which means that there are prevalence of right molecules. The phase is 0. When the enantiomeric axis is positive, the prevalence of left molecules, the enantiomeric axis positive, prevalence of left molecules, phase jumps by pi. Now what we did, we added noise to our simulation, and the noise here, the only reasonable source of noise that could be is a fluctuation of laser intensity, so it's now 10% intensity fluctuations included, and this is already with the noise. And here the red is the curve which includes noise, which is quite strong. So what you see here, you see the example of robustness, which shows up in the fact that because of this sharp jump between the left and right geometries, you can easily distinguish even small amounts of enantiomeric axis because of this very large derivative. So we were really happy about this, but then we discovered that actually in the experiment it's not so easy to make a perfectly circularly polarized light, and it means that there will be a mixture of elliptical light. But if there is a mixture of elliptical light, it means basically that you have right circularly polarized light and a little bit of left circularly polarized light. And this changes the topology of our topological number. So we suddenly, for a small admixture of, say, ellipticity of omega field, we get two topological charges, 6 it was before, and 2 is the new one. And the question is what to do in this case. And if we want to save the situation, we need to find a way to separate the topologies. And that is what we have done. So what you can do, basically, if you have the ellipticity, you can take advantage of it. You can change the phase between, say, co-rotating and counter-rotating components. And what it does in reality, it just rotates the polarization ellipse. So the phase between these two components can be controlled in the experiment, and you can do different measurements by rotating the ellipse and by Fourier transforming with respect to this phase of rotation. You can actually separate different topological charges. So this is the result that we got. We wanted to separate the topological charge 2. And we see it here. So there are two blobs now. They rotate in different directions, just like expected. And another aspect of the case when the light is not perfectly circular is that it also is globally chiral, which means if I take the signal all over the interaction medium, the light is having the same handedness everywhere, and it means that I can have stronger anti-sensitive signal in intensity, not just in the direction, but also in the intensity, total intensity of the signal. Okay, so now the second story about the topology in ultrafast electronic response. And I apologize for this oversimplifying reminder, but I just wanted to remind you about the key geometrical quantities which you meet whenever you would like to characterize topologies. And these are geometric phase and the curvature. So basically, in topology, we would like to characterize shape in somewhat abstract way, which means that we should be characterizing them as if we are living on them, as if we cannot look from them aside. So in this case, you can see that indeed you don't need to leave the surface if you want to characterize its curvature. You can just do it by walking on it, and as you walk, you may either accumulate the phase, or you may not accumulate the phase if the surface is flat. So this is the geometric phase, and the curvature is a local quantity which kind of tells you about the density of geometric phase per unit square. Now, what is important, that topological invariants that distinguish different topological objects, they are obtained from curvature, and phase can also be the topological invariant. So now, why would you care about it as physicist or as chemist? Is because it has implications for dynamics of electrons in the configuration space. Imagine, for example, that our configuration space is set up by two angles. And then our configuration space is torus, and it obviously has a certain topology, interesting topology, or maybe not interesting. And what happens is that our electrons, they move in this configuration space. But because the configuration space makes sure that these electrons have to turn, so the electrons will turn, but the charges which move on curved trajectories, they generate fields, magnetic fields. And this magnetic field basically encodes the geometry of the space and the topology of it. So the curvature is one of such fields, and it's known to lead to new observables in solids. So the question is, does the curvature exist in chiral molecules? Does it lead to new observables? And what is the appropriate configuration space in this case? So let us start with a simple action. Let us excite a superposition of electronic states in a chiral molecule. We'll use short pulse, and there is a superposition, and superposition means that there is an electronic current. So now let us look now at what kind of current we have excited. Okay, I told you already what I wanted to tell, so it's going to be ultra short pulse, which excite a coherent superposition of two states, and we do it with circularly polarized light. So this is the current that you will see in this situation, and that will be in the left molecule, that will be in the right molecule. And what you see is that the current is chiral because the vector of current traces a chiral helical structure. So now we can explore configuration space which is relevant for these temporal structures. You again see the example of local chirality. So it's chirality which evolves in time. It's a geometric structure which is reflected in time, in temporal evolution. Now, the configuration space. Well, we are dealing with randomly oriented molecules, and if we irradiate randomly oriented molecules with circularly polarized light, then this is the interaction. So there is a dipole coupling to the laser field, and obviously that depends on the angle between the molecule and the laser field. We can also represent it in the following way. We can go from the lab frame to molecular frame, then molecular is fixed, and the laser field comes from all different directions. And now we see that because, of course, the excitation process is very sensitive to mutual orientation of molecule and the laser field, then we have a coupling between electronic and rotational degrees of freedom, which is created via the interaction with the laser field. So it's not a Coriolis coupling, it's something which is completely controlled by the laser field. Now, what you get is the following situation, that each of these fields will introduce its own temporal current. And then you can ask a question, so is there any global geometric property which is associated with these currents for different molecular orientations? And in particular, the way to think about it is the following. You could solve a Schrödinger equation for every of these orientations, for each of these orientations. And you would find some wave function describing these currents. But the phase of this wave function will be not defined between these two configurations. So the question is, should it be defined? Is there any phase that connects and characterizes this joint space? And is there a curvature of configuration space of molecular orientation for randomly oriented molecules? So the answer is that there is a connection which is given by the gradient of the wave function that you calculate with respect to the laser field. There is a curvature which exists only in chiral molecules and only if currents are excited, or otherwise if time reversal symmetry is broken. And as usual, this is a curl of connection. And finally, there is also a geometric phase associated with the curvature, but only if the flux of this curvature through this space is non-zero. Now, the geometric phase also has a clear physical meaning. Its value is given to an anti-sensitive photoionization or photoexcitation yield. So now what is important is that, of course, I want to show you new observables, because whenever you have a new quantity, such as this curvature, it may lead to new observables, and it does. So the curvature is dynamic property, and it expresses the electron dynamics in photoexcitation or photoionization. And dynamics offers us control over the geometric field and phenomena that it induces, and it leads to new and anti-sensitive effects and new observables. So what are the observables? So the curvature can be related to a geometry of bound states, and this happens if you perform excitation with circularly polarized light. And then you excite a chiral current, just like I showed to you. It expresses the existence of this curvature for this particular excitation of propylene oxide LUMO and LUMO plus 1. Curvature is oriented this way in the space of molecular orientations, and it leads to the existence of any vectorial observable in the cation. In particular, it leads to molecular orientation. So if you perform ionization, then what you find is an anti-sensitive orientation of molecules along this curvature. So what is the meaning of this effect? It means that you have laser field for the molecule coming from, you have in the lab frame, you have molecule oriented in different ways, and Berry curvature in each molecule in molecular frame the same, but in space different. Then you come with the laser pulse, and if the propagation direction of the laser pulse is the same as the orientation of the Berry curvature, those molecules will be preferentially ionized. As a result, you get oriented ions. The effect is large. It leads to 60% orientation. And here you see the angle between the... So what you will have is that these molecules will be oriented such that, for example, this vector aligns with... This vector is aligned along the propagation direction of the laser field. So, for example, in this particular case, you would have, say, 65 out of 100, you will have 65 molecules looking like this, and 65 having this vector in the lower hemisphere. Now you can also excite the curvature associated with the continuum. You can associate it associated with the current excited due to photoionization. And in this case, it depends on K in non-trivial way, and the orientation overall is lower, but the curvature traces an interesting, goes in different direction if you consider different K. So basically, you have a control over orientation of molecular ion just by exciting superposition of certain states. So what is interesting, so these calculations were done for propylene oxide, excitation of LUMO and LUMO plus 1. You can also do it, and Bernard Pons did the calculation for a different molecule, for methyl lactate, for experimental situation realized in this experimental setup, which was recently published. So you have a linearly polarized pump, and then ionization with circularly polarized pulse, and that corresponds to this setup where the curvature appears due to continuum currents, helical currents. So now what is plotted here, of course, the quantity, the orientation, and this is the degree of orientation on the axis. So the quantity will depend on the delay between pump and probe pulse, and you can choose a specific delay to maximize the quantity, but it will oscillate, which means that the orientation of the molecular ion depends on the direction of the electronic current. And that is, for my field, for the field of attosecond physics, this is an important concept called charge-directed reactivity, when the electronic current can define the later dynamics of the nuclei. And if you want to pursue this idea further, you can realize that if the ion is created in the excited states, there will be a fragmentation, and the direction of the fragment injection will be fully controlled by this curvature or by the current. Okay, so this is just a very, very new results, virtually a few days ago. So we are also working on exploring the link between geometric magnetism that I presented and the spin. And of course, it's an obvious way to follow. And because the Berry curvature requires the breaking of time reversal symmetry, and this you can achieve if you include spin-orbit interaction. So what we found out for our little chiral model with coupled spins, coupled spin-orbit interaction, is that the curvatures for the spin-up and spin-out, spin-down electron, they can be very different, which means that you can create a situation in which the propagation vector of light is aligned with only one of these vectors, and then you have again the same effect that I explained to you before. There is enantiosensitive orientation, and plus the ions are selected on spin. So spin polarization on top of orientation. So finally, I have probably, 12 minutes. I will tell you very, very briefly about linking chirality and topology in non-Hermitian dynamics. Well, we know that in non-Hermitian systems, the conical intersections that we see here for a normal Hermitian system, they look differently, because what happens is that not only energies become degenerate, but also the eigenstates coalesce. And that means that dimensionality of your dimensionality of your Hilbert space basically shrinks, and sometimes this is associated or named topological transition, but it's a matter of taste. There is certainly topology just like here, and the topological properties of the transitions from one surface, potential surface, to the other, they are quite different. For example, we know that for a Hermitian case, the adiabatic theorem tells you that if you evolve the state adiabatically, then we remain in the same state. Here is a completely different situation. You will necessarily end up in the second state. And this is, of course, unique to non-Hermitian systems. If you consider not just adiabatic, but in general, including non-adiabatic transition, then you will have another curious phenomenon that basically population transport between two states really depends on the direction of encircling the exceptional point. And what would be interesting is to make these exceptional points enantiosensitive. Then you could encircle the in one enantiomer you would encircle the exceptional point, and the other is not. So what is interesting that if you drive the system with synthetic chiral light, you make your exceptional points, these points, topological points, you make them enantiosensitive. So how does it happen? So this is a simple example of the system which is both chiral and non-Hermitian. It's chiral because it has 3 levels. This is the minimum amount of levels that you need to describe chiral system. I will explain why in a second. And it's non-Hermitian because this level, the 3rd level, electronic level, is in the continuum. So there are 3 levels coupled through the 3 laser fields and through the transition to the continuum. So in other words, there is ionization going on all the time. Now, the fields that couple the system, they satisfy this property that I told you before, that they are non-complanar, and probably the best, they are mutually orthogonal, coming from all 3 directions. And now what you see here is the quantity which characterizes the chirality of this 3-level system, established first in the seminal work by Kral and Shapira. And what you see here is simply a product of dipole coupling times field. And because all the states are coupled, this is a signature of chiral system. You see there is no parity here. Okay, so this is a chiral coupling, and it changes sign if you go from left to right enantiomer. And in randomly oriented molecules, it is expressed in a nice way, where you have a triple product of dipole expressing the molecular handedness, molecular pseudoscalar, and chiral correlation function, which expresses light-handedness. Now, if you write the equation for enantiosensitive points for this system, you will see that this chiral coupling comes into play, which means the position of exceptional points in the system is enantiosensitive. And there are just few last slides. So what you see, position of points, I did not really explain properly, that to do this encircling, you do it, of course, in the parameter space. And I failed to tell you what is the parameter space. So as a parameter space, for example, you can take detuning, for example, of this photon, omega-3, and the strength of the field at the frequency omega-3. Now we are looking at this space, so there is a strength of omega-3 field and detuning on this axis. And what we find that exceptional points in this space for right molecules and for left molecules, they are basically mirrored to each other, which means that if you do a loop encircling this point, and this is the loop that I explained before, this is the loop that either brings you from one state to another or doesn't. So what you will see that you will encircle, and in the right system you will perform a state transfer, and in the left not. And this is a situation where you will have a mixture, and in a situation where you will have exact same pulse. So in one case you will see transfer and the other not. And what you see on this figure is precisely this. So we have 2 states, and in right enantiomer there is a transfer, and in the left enantiomer nothing happens. Of course, you see here 100%, but this one has to realize that it's always a trade-off between the efficiency and loss. Because as this all transfer is happening, the system is losing the population to the continuum, because it's non-Hermitian system. So there is loss, and what I'm speaking about right now, loss which is equal for both states. So it means that, and to do a loop, you want to be slow. The slower you are, the more you pump. But the slower you are, the more you lose. So you need to find a trade-off, and we found we could achieve, say, 20-30% population transfer without searching too much. And this is my last slide. I would like to tell you about one very nice topological connection, enantiosensitive and topological connection in photoionization. Basically, you can find that photoionization dipoles of chiral molecules have very interesting singularities, phase singularities. So there are points. So what you see here is a sphere in momentum space. So this is the energy shell corresponding to photoionization of H2O2 molecule. This time it's oriented. And energy shell means that energy fixed, but direction of momentum can be arbitrary. And in left and right molecule, you can find a point in which you have phase singularity. So it's a phase vortex. You see that phase goes from 0 to 2 pi once, and here also once, but they go in opposite direction. So what underlies this phase singularity is the following behavior of the photonization dipole. So photonization dipole is a Möbius strip independently on where you look here, and you will have left Möbius strip in left molecules and right Möbius strip in right molecules. So the phase of photonization dipole turns out to be an anti-sensitive topological invariant. And you can, in principle, another second field, you can resolve photonization dipole both direction and the phase and the amplitude. So in principle, this is not, I mean, it's obviously tedious, but it's not impossible. And what result is that this is actually a proper topological invariant, which means that if you do this experiment for left and right molecules, in this because they are not in the same point, in this molecule, again, we will encircle and the phase will actually quantize, and in this one, not. Thank you very much for your attention.
Thank you, Olga, for a fantastic talk. Questions?
Hi, Olga. Thanks for a fantastic talk. So I want to ask you, so you always talk about the photoelectron spectrum. Is there a chance of seeing any of these effects in the dissociation spectrum? So the electron wave function gets shaped in such a way that the molecule breaks up, because you had the orientation shown. So maybe there it could be possible to see.
Yes. So basically, this is the last part that we did quite recently is to. So the first geometric Berry curvature that we found was associated with the continuum. So now we have also this one, and you basically have the same expression that you can use to compute them and plot them and to analyze them. So basically, you take a wave function, you take gradient with respect, you solve it, we just solve it using perturbation theory, you take gradient with respect to field, then you take a curl, similar way, and then you depending on what your wave function is, it can be dissociation, it can be bound state, it could be continuum, it could be virtually anything. What matters is how non-trivial is your space. So basically, what we now starting to understand that basically the way how it connects to topology is that you can, well, it's probably too complicated. The answer is yes.
Okay, thank you. So there's no fundamental thing against.
No, on contrary, exactly with this bound states, I think that's what we want to explore now with the Berry. Oh, now I'm going in the wrong direction. Anyway, in the Berry curvature in the bound state, we want to explore the interplay of this topology with the topologies that you can see at the conical intersections and stuff like this. But it basically all light induced.
I have more questions, but I'll ask you in the break to let more people have a chance.
Another question?
Thanks for the talk. So firstly, it's extremely impressive how quickly you're progressing in the last year with this concept. So in the beginning, you said that the end goal is to be quick and precise with this distinguishing of the chirality. So would you say that you've reached the chemical methods in terms of the precision of really being able to say what is the mixture?
Okay, so so first of all, of course, I can't say this, it would be too strong statement, and this needs to be done experimentally. We have done computationally, so we were definitely here sensitive. If you do calculation for, say, 1%, we are sensitive to it. Right now, there are other methods from the electric dipole family, and this is photoelectron circular dichroism. There has been papers showing that you can reach 0.1 accuracy in establishing an antimeric axis. So it gets pretty accurate, and of course it's very fast. And what I know, actually another my dear colleague from Technion taught me this, Herman Wollesker. They have written this amazing paper in Nature Chemistry about an antimeric axis as a biomarker. And in his opinion, with this progress that the whole umbrella of the electric dipole revolution methods offers, it's about 3 orders of magnitude. He thinks that even if it's 1 or 2, that would be already probably enough for them to start to see something in real molecules.
Okay, thank you very much. I think we need to move on. Thank Olga.